Back, everybody. How's everyone doing? Good coffee? Yeah? Okay, so this next lecture is going to be about system identification. And this is such a short amount of time to tell you anything meaningful at all about system identification. System ID is an extremely rich field. It's been in full force for at least the last 50, 60, 70 years. And so I'm going to tell you about the most kind of briefest part of system identification. So I'm just going to give you a kind of blanket definition statement. System identification is learning a dynamical system model from measurement data. Okay? That's it. You don't start with a model. You have to build your model from your data. That's what system identification is. So you collect measurements, you build a model of those measurements, and again, we're always interested in the balance between accuracy and efficiency. Okay? There is a dual side of this. You can't really talk about system identification in a fluids context without also talking about model reduction. And I see these as being very related, almost dual concepts. Model reduction is where you do have a model, Navier-Stokes or something similar, but you want to simplify it because the original model is too big or too complex for whatever objective you have. Okay? And these are related. You use a lot of the same tools and techniques, mathematical architectures for system identification and for model reduction, but they start from different places. System identification is purely data-driven. Model reduction, you start with some governing equations. Okay? And I have thought a lot about what to talk about today in this hour because it's such a brief time. I actually prepared a bunch of whiteboard, but I figure that I only get one shot on this whiteboard. And so I'm going to punt a little bit, and what I'm going to point out is that there are two chapters on classical system identification, linear system identification in the book I just wrote with Nathan Kutz. And so I'm going to just completely punt. You can download the entire book at databookuw.com/databook.pdf. So this is not just a shameless plug. Like, you can download this PDF, and all of the system identification is in this book in chapters 9 and 10. And all of the lectures for all of that classical linear system identification are on YouTube. And it's 5 hours, 6 hours, 7 hours. So I'm not going to try to compress that into this 1 hour. Okay? It's very technical, and it requires a whiteboard. So what I'm instead going to do is I'm going to give you the very high level of what kind of classical system identification does. And I think what'll be more interesting for all of you, and will segue much more naturally into tomorrow's lectures on machine learning, is I'm going to talk about what are the modern cutting edge tools in system identification that we're using today. Okay? Good. All right. So again, I would probably say that 90% of the techniques in system identification are for linear system identification. Why is that? Because it's all that we can work with and have any kind of guarantees or generic tools. Linear systems are the only systems where I have one-line solutions in MATLAB for control and estimation. I mean, all of you have heard of the Kalman filter. And a lot of the modern era of work on system identification started with Kalman and Kalman filtering, okay? So I'm just gonna have like 2 or 3 slides on linear system identification, and then I'm gonna move to more modern stuff. So here's a system. So the basic idea of model reduction or system identification is, this is a model reduction problem. Here's a model, it has 2 states. Do I need to pay attention to both states? Are both states equally important? If I only had enough computational power to pay attention to one state and to simulate a one-state ODE, which one would I pick? This is like a real simplified version of what you're going to face every day in fluid mechanics. You have 1 billion states. What states do you pay attention to if you only can afford to pay attention to 5? Okay, so just any thoughts? Which state matters more, X1 or X2? How many of you think X1 matters more? How many of you think X2 matters more? Okay, why do you think x2 matters more? I would completely agree with the x2s because it has a slower time constant. x2 is going to be around a lot longer. It's our future. Okay, x1 is going to die out long before x2 does, so we're going to have to pay attention to x2 for longer. So if I only get to keep one state, I'm going to keep x2. Except this is not the whole story. Okay, I gave this example to trick you. What if I have a control input and a measurement output? Now which state matters more? Clearly x1. Even though it's more damped, and if I only looked at the A matrix, x1 would be the less important mode. Now that I have control inputs and measurement outputs, clearly x1 is far more important than x2 because x2 is barely affected by my control input and it is barely observable by my sensors. It practically doesn't exist to my control system. Okay, so you have to really think about a lot of different things when you're doing model reduction. There's a whole field of model reduction called balanced model reduction. This started in the 1980s with Moore, and then it entered fluid mechanics with Wilcox and then Rowley in the 2005 time period. And there's a bunch of great papers on balanced proper orthogonal decomposition. Basically, how would you find modes? So remember, you have your big fluid, and a way of finding a few numbers that matter would be the POD. So Barrett has showed you, who did POD? Okay, so you saw the POD, Scott did POD. So you know that that's one way of doing model reduction. You have a million-dimensional system, you do the SVD or the POD, and you get 5 or 6 or 7 states out that matter. But again, that only was half of the story. That if you had control inputs and measurement outputs, those might not be the best modes. And so instead, there's this idea of balanced model reduction, where there are these things called observability and controllability gramians, which tell you in your high-dimensional state space which states are most controllable and which states are most observable. So if we go back to this system, the x1 state is far more controllable than the x2 state, and the x1 state is far more observable than the x2 state. And so that would basically say that certain directions are much more observable and controllable than others. And so what the balanced POD tries to do is find a coordinate transformation into a new coordinate system. Remember, just like the eigenvector coordinates, you're trying to find a coordinate transformation into a new system. And these are eigenvectors of another matrix, where these gramians are equal and diagonal. And then you basically keep the directions in state space corresponding to largely observable and controllable directions, and you throw away the weakly controllable and weakly observable directions, like in that simple 2x2 example. So that is a huge field of work that people do every day. That's all I'm going to say about that. Okay, except this is just one little example of how to do this. Okay, so let's say I have this system here, x1 equals -1, -10. So the x1 dynamics stay around longer than the x2 dynamics. And you'll notice that my actuation matrix and sensor matrix are kind of opposite of each other. So the x2 direction is much more controllable, and the x1 direction is much more observable. So I want to find a coordinate transformation that balances these two. And I like this example because to some extent, I chose this to be an issue of units. I basically said, okay, let's say I am measuring Z1 in like millimeters, and I'm measuring X2 in kilometers, so that all of these numbers are just messed up. So all I'm going to do is I'm going to introduce this coordinate transformation that scales X1 up by 10 to the 3 and x2 down by 10 to the -3. I'm not going to get to eat this. And if you introduce that, this is the balancing transformation I talked about. Now what you have is a balanced system where the control and the sensing are equal to each other. So now if I wanted to truncate the system, which one would I truncate? The ball's in your court. Which state in Z coordinates would I truncate? I would truncate the Z2 because all things being equal, now they are equal, these are equal and they're equal to each other, and it's all decoupled, the Z2 dynamics are going to die out much, much more rapidly. So I'm going to see their effect less. So if I only kept the Z1 equations, I would keep most of the input-output dynamics. So that's what this balancing does for you. It allows you to then make your decision based on the matrix A again. Okay. Good. Okay. So, this was the picture I showed you before, system identification, model identification. That's all I'm going to tell you about model reduction. Now I'm only going to tell you about system identification. Good. And again, back to our lecture on dynamical systems, there are kind of three big challenges that I think about a lot in system identification. One is, our equations are unknown. So that is the whole foundation of system identification, is discovering these. The second piece is that our nonlinear dynamics are poorly understood. So if in the process of discovering my model, I can also discover some coordinate system where that model becomes simplified, I want to do that. Okay. And high dimensionality is a big problem. Okay, so we're always going to be doing something like POD as the first step of this. Okay, and so I'm going to mostly focus on the first bullet of discovery here. Okay, and I'm going to walk through a few different things. So you have heard about dynamic mode decomposition, yes? All right. Peter Schmidt told you about dynamic mode decomposition. I'm going to give like 2 slides because it is a system identification technique, and I want you to see it as a system identification technique. Then we're going to talk about Koopman operator theory, which is kind of one of the main use cases of DMD. Then we're going to talk about nonlinear system identification. How many of you have heard of Koopman operator theory? Okay, everyone. I'm assuming Peter probably mentioned it. Good. All right, so I'm going to talk about it a little bit. So this is just a bunch of examples of dynamic mode decomposition. It's a little nerve-wracking to give this lecture with Peter here because he invented the dynamic mode decomposition, and I'm just, we're basically just users. So remember, we think about dynamical systems as movies. Okay, that's what they are. They're movies. They vary in time. There are frames in a movie. And so I can take my flow past the cylinder. I can take every frame in this movie and arrange them like this. I can then build these matrices X and X prime, where each column of X is a frame of my movie that's been reshaped into a very tall, skinny vector, a million-dimensional vector. Okay, and each column is the state of my system evolving in time. Okay, so this is the kind of data you might have access to when you're doing system identification. DMD is one approach to build a model from the kind of data you would be using for system identification. I have a time series of snapshots of my dynamical system, and I'm trying to build a model to describe the evolution. Okay, and as you know, the DMD is essentially this least squares regression, this best fit linear model that advances X into X prime. Each column of X, it would advance those columns forward one time step forward in time. So you've seen this before. Now, DMD has some super cool features because this A matrix, if X was a million tall vector, then this A matrix is million by million. And so you don't want to compute it. You don't want to put it in memory. You especially don't want to compute its eigenvalues and eigenvectors, right? And so the DMD is a set of extra linear algebra techniques to find the leading eigendecomposition, the leading eigenvalues and eigenvectors of A without ever actually computing it. And so, for example, you compute an SVD of X and you work in this reduced subspace, right? Good. And that's what we do in a lot of system identification techniques when you have high dimensional data, is you first find some low dimensional space where you can project onto. Okay. I stole this slide from my wife. This is how she thinks of the DMD and explains it. It's like if principal components in space and Fourier transform in time had a baby, it would be adorable. And, these are two of the most important algorithms of the last century. Okay, so it's no wonder that DMD is extremely useful and is being used in, lots and lots of fields beyond fluid mechanics as well. Okay. Good, but I think of this as a system identification technique where you get a linear system, x prime equals ax. Okay. This is the original paper, and there's some fantastic examples in here. I really think you should read this, and I'm not just saying this because Peter's in the audience. I really, really love this paper. There are individual sentences buried on like page 12 and page 17 that you could find an entire paper to write, and so that's pretty cool. After the original DMD paper, of course, there was a strong connection to Koopman operator theory, to nonlinear dynamical systems. So you should be wondering in the back of your head, why are you saying that you can model a nonlinear dynamical system like Navier-Stokes? We know that that limit cycle is a Hopf bifurcation, so there's some nonlinearity happening in this flow. Why can I model that using these linear evolution operators? And so it's this deep connection to Koopman operator theory that I'm going to tell you about later. That I think makes this a nice story, and this was developed by Rowley and Mezich and collaborators. There's a cool video. I stole this from my wife. She makes way cooler DMD videos than I do. So she gets this question all the time about what's the difference between DMD and independent component. How many of you have heard of ICA, independent components analysis? Okay, it's like a statistics tool for separating sources that have different dynamics like this. And so this is what PCA would give you. It mixes those two signals, right? Because PCA is only based on the energy or the variance in the signal. And when I say PCA, you should also be thinking it's the same as POD. Okay. ICA actually does separate out the square and the Gaussian that are oscillating at different frequencies, but it has a bunch of noise and clutter. DMD perfectly separates them, and it gives you the eigenvalue of how those dynamics evolve. It gives you a model, not just the modes. Okay, and since its origination, it's been applied to tons of different systems, weather and climate, neuroscience, lots of other fluid systems, disease modeling now, robotics, and things like that. So, and one of the things I will tell you later on in this lecture, one of the things I like about DMD is it is a very simple formulation of an important problem in terms of linear algebra. And if I can give you one piece of advice, and I'll probably give you this again, you should become linear algebra ninjas. That is like the most useful thing you can pick up, is good skills in linear algebra. If you can pick up 2 things, get really good at optimization. And if you have time for 3 things, learn statistics too. Okay, but linear algebra is everything, especially in model reduction and system identification. And the DMD formulation has been extremely extensible. It's easy to extend it to include control and partial outputs and nonlinearity and all of these other aspects. So I think of it as kind of this unifying framework. And it actually ties into decades of system identification research that I'll tell you about. Okay, so how many of you have heard of the eigensystem realization algorithm or the singular spectrum analysis? Okay, from climate science. There are deep connections between DMD and those classic techniques. Okay, good. So this is a little dangerous because I actually don't know how much you know about Koopman operator theory. So I'm just going to give you what I think is important from Koopman operator theory, okay? And for me, it's all about the discovery of coordinates. So system identification is about building models from your data, okay? And I see model building as having 2 equally important legs, okay? One of them is building the model itself, like what is f of x? The other part that's equally important is what are the right coordinates to build your model in terms of? You might measure x. How do you know that's the right variable to build a model on? Right? Like in fluids, we have some theoretical justification that vorticity might be a good variable. Okay? But in lots of systems, it is not obvious what variable you should be using to build your model. Even in planetary dynamics and astrophysics, it took thousands of years for humans to discover the right coordinate system to describe the model for the motion of the planets. Okay, that was a coordinate system. And so that's what I'm going to talk about with respect to Koopman operator theory is This is a way of finding a coordinate system where your nonlinear dynamics becomes simple and linear. Does that, everyone follow? And again, please interrupt me if you have any questions. This is confusing as hell the first time I thought about it. So we're going to now be talking about this part of the system identification problem. Nonlinear dynamics are very poorly understood, and we want to build coordinate transformations where our systems become simpler. And in this case, when I say simple, I mean linear. And it's kind of this miraculous statement that shouldn't, be obvious that it's true, that for large classes of nonlinear dynamical systems, pretty much almost all of the nonlinear dynamical systems we're interested in, there are coordinate systems and coordinate transformations, ways of viewing the system, where even very nonlinear dynamics look linear. They look like exponential growth or decay in sines and cosines in those coordinates. And this is a theorem from Bernard Koopman, 1931. He wrote this down. So he was trying to help build the mathematical foundations of quantum mechanics, Hilbert space, and relate Hilbert space and dynamical systems. And in doing so, he realized that if you have a nonlinear dynamical system, there is a Hilbert space, this infinite dimensional function space of all possible ways you could measure that system. So I've got a system dynamics, x dot equals f of x, super nonlinear, but I can measure that system in an infinite number of ways. I can measure x1 squared times x2, or x3 sine x1 cosine x2. There's an infinitude of ways of measuring that system. It forms a Hilbert space. And what Bernard Koopman showed is that the nonlinear evolution in state space becomes a linear evolution in this infinite dimensional Hilbert space. So your nonlinear dynamics are linear in an infinite dimensional measurement space. That's this paper here, Hamiltonian Systems and Transformations in Hilbert Space. A little bit of history. It turns out that the Koopman operator theory was the missing piece that was used to solve the ergodic theorem by von Neumann and by Birkhoff independently. So for those of you who remember, Maxwell and Boltzmann described the statistical description of gases. And the Koopman operator theory was the missing piece to tie up the mathematical theory, and that's what von Neumann and Birkhoff did in the same year that Koopman wrote this paper. Okay, so super important at the time. There's a nice history in PNAS about this. And so at the time, no one realized that this was important for nonlinear dynamical systems. This was useful for the statistical theory of gases. Okay, and it's only recently that Koopman theory has had this resurgence. And a lot of it is due to Igor Mezich and various colleagues and collaborators. And actually, I would argue a lot of it has to do with the DMD, because that's the engine we use to find these coordinate transformations. Okay, so when I say that there is an infinite dimensional linear operator that involves all possible measurements I could take of my system, you should be thinking, when I say infinite measurements, you should be thinking big data. Okay, we're collecting lots and lots and lots of measurements of complex systems now. We have more measurement capability than we've ever had. And the idea is that the more measurements you have, the more linear your system becomes. And it's a very powerful perspective. So this is almost philosophical at this point. I want to show you on a very concrete example. Okay, and how many of you have seen this example before? Okay, good. So I'm going to walk you through this. This is a very simple nonlinear dynamical system with two variables, x1 and x2. In fact, the x1 equation is linear. x1 dot equals mu x1, just linear dynamics in x. x2 is only a little nonlinear. It's lambda x2 minus x1 squared. And I'm going to assume that lambda is a fast eigenvalue and mu is a slow eigenvalue, just because it makes my conceptual life easier. So what that means when lambda is fast means that x2 very rapidly equals x1 squared. And so initial conditions will quickly attract onto this red manifold and then slowly go to the origin if they're both stable eigenvalues. Okay, so this red thing is called a slow manifold, and the dynamics rapidly equilibrate onto this. So that's what the dynamics do. And what I want to convince you is that there is a coordinate system that if I wrote these dynamics in this new, better coordinate system, everything would become linear. Okay, and here's the coordinate system. So I'm going to build this three-dimensional system so that y1 is x1, y2 is x2, and y3 is this nonlinear function x1 squared. And we're going to go through these operations and make sure that the dynamics in y coordinates are in fact linear. Okay, and why do I want linear dynamics? Because we're lazy. We want to use one-line MATLAB commands for optimal control and optimal state estimation and future state prediction. I don't want to simulate this thing and do nonlinear optimization, right? I like one-line commands. So I want linear systems. Okay, so y1 dot is x1 dot is mu x1, which is mu y1. So that's still linear. The y2 dynamics are interesting. y2 dot is x2 dot. And x2 dot is lambda y2 minus lambda y3. Okay, so that linearized my second equation. And all of the kind of magic happens in this third equation. So what is the derivative of x1 squared? Well, it's 2x1 x1 dot. And 2x1 x1 dot is 2 mu x1 squared. And 2 mu x1 squared is just 2 mu y3. So y3 dot is closed in this coordinate system. Its derivative is also in this coordinate system. And so I really get this linear 3x3 system that describes these nonlinear dynamics. Okay, there's no magic here. It's pretty simple. And here, are the trajectories, the same white trajectories in that three-dimensional space. These are linear evolution dynamics. And when I project them onto the y1, y2 plane, you can see that they have this same behavior here. Okay, so nothing magic is happening. And it turns out that for all nonlinear dynamical systems, there are some coordinates where they will look linear. And our job is to find those coordinates. And that is really hard. Okay, if it was easy, I picked the one example where I can do it easily. Okay, it's really hard to find, in general, these coordinate transformations where this works. But does everyone appreciate why we want to do this? It makes our life so much easier to make things linear. Okay, and I'll point out that if you look at the left eigenvectors of this matrix, you get essentially these nonlinear observables, x1 and x2 minus bx1 squared. And if you measured your system in these phi coordinates, phi lambda has dynamics that look like e to the lambda t, and phi mu have dynamics that look like e to the mu t. They really are linear if I view the world in those coordinates. Okay. Okay, good. So why doesn't this work? We're going to talk about this equation. Now this one looks even simpler. X dot equals x squared. Can anyone tell me what this system is defined? What characterizes this dynamics? I'll give you a hint. You can't talk about it in an airport because it blows up. In finite time, okay? So I can only talk about this after I land. So we're going to try the exact same trick. We're going to try to build an augmented state vector with some nonlinear terms so that our dynamics close. And so since I have a right-hand side x squared, I'm going to try to put an x squared in my dynamics, okay? And it's nice because y1 dot does in fact equal y2, so that's good. But now when I compute my ddt of y2, I get 2xx dot, and now I get 2x cubed. Shit. So now this is not in my space. So the derivative of y2 is not some linear combination of y1 and y2. So I need to add a y3, which is x cubed. And when I take its derivative, I get an x to the fourth. So I need to add an x to the fourth. When I take its derivative, I get x to the fifth, and so on and so forth. It doesn't close, ever. So Koopman says that you get linear dynamics, but you really do need an infinite dimensional basis in general. It's only linear in an infinite dimensional representation. Okay, so this is the rub, is that we want to find these magic coordinates, but we can't often, or at least we can't represent them in easy coordinates. Polynomials are like as bad as you could possibly use for coordinates. I mean, most of you know that, but it's an illustrative example. What is interesting is that if I truncate this system at order 2, order 3, order 4, we do get closer and closer to this observed finite time blow-up behavior, but it really doesn't do the job. Okay? So I showed this to Clancy Rowley. We were waiting for a bus to go to a workshop in Florida. And he literally just scratched on a napkin the solution.